appreciate if you interrupt me and ask questions, make clear if there's anything you don't understand. And I'd like to stress, if you ask anything or make a remark, please speak loudly so the other people in the audience can also understand it. Because I experienced myself, it's not always easy. Good. Well, I would like to end up, well, this series of 3 talks by telling you about some recent work on one-dimensional hydrodynamics. And maybe your reaction is, well, one-dimensional, how dull can that be? Well, it turns out to be a very non-trivial system. And so, to my feeling, it's very exciting that apparently one can make completely exact statements about the long-time behavior of, for example, heat conduction or sound damping and propagation in these one-dimensional systems. But to prepare you for that, I want to start in this lecture by introducing hydrodynamics to you. And to do it in a compact way, I want to do that through the Green-Kubo formalism. Then there you can find an extensive set of lecture notes plus sets of problems. I think some quite good problems. There is a slightly condensed version of these lecture notes on the website of this school. But, well, there's much more in there which I won't talk about at all. Even lecture notes for the school I won't cover completely. But I think they're very useful to fill in the gaps if, well, you miss something or if you want to understand it in a slightly more greater detail. Then my second talk will be about long-time tails. These are slow decays of current correlation functions, which are determining the transport coefficients in the hydrodynamic equations, and a bit about mode coupling equations. And then all of that will be used in my final talk on one-dimensional hydrodynamics. Plus how this is connected to the KPZ equations for one-dimensional systems. Good. Statistical mechanics always is concerned with, well, the properties of systems of extremely many particles. And so if you talk about non-equilibrium situations, you have systems with 2n d and the number of particles, d, the dimensionality of the system. And I think about them in classical terms, where n is in the order of 10 to the 26 or something like that. Degrees of freedom. Usually they're coupled, and unless you can find some smart trick to decouple them into independent variables, which is sometimes possible, but usually it's not, these equations are hopeless to solve just by their number already. Then, if you want to describe these systems on a macroscopic time and length scale, you take recourse to the hydrodynamic equations. These equations look at the densities of conserved quantities, particle number, energy, momentum, and they give predictions of how those will evolve in time for, well, a given initial situation, a given density field, velocity field, temperature field, and these are, well, fairly simple equations. They're not simple to solve, but the equations themselves are not so hard. So how do you get from here to there? Now the intuitive idea people have developed around, about this is that there is really a matter of a time scale separation. So typically, if you look at a fluid, a liquid or a gas consisting of many, many particles, then locally, on pretty short time scale, the distribution of the velocities will become very close to a Maxwellian. With maybe slight corrections due to the non-equilibrium features of the system. But a local equilibrium distribution of the velocities in almost all cases is reached very soon. And then the parameters that determine this distribution are the density, the energy density or temperature, and the local velocity. And then on a much, much longer time scale, these hydrodynamic fields will decay to equilibrium in a dissipated way, which is a bit mysterious because the microscopic equations of motion are time reversal invariant. The hydrodynamic equations are not, but we think we have a fair understanding of that. But okay, I want to face the question, how do you get from here to there? And what I will use for that is the Swansea-Mori projection operator formalism. And this is completely based on this notion that there is a time scale separation between the decay of all, well, functions which are, say, in a way orthogonal to these hydrodynamic densities and the hydrodynamic densities. And on long time and length scales, you can use these hydrodynamic densities to characterize the system completely. And that is an assumption that goes in. It is completely based on physical intuition. It is demonstrably not always true. There are, I'll come back to that, very common situations where, say, these assumptions that only these hydrodynamic densities are slow is not correct. But in many, many cases it works, and it gives you, at least in linearized form, the hydrodynamic equations with formal expressions for the transport coefficients that occur in them. And to simplify matters to start with, I will first consider tracer diffusion. This is the phenomenon that you have a single particle, or you have a very small density of non-interacting particles that are all of the same type, which move in a background that, in the simplest case, is in perfect equilibrium, except for the presence of these tracer particles. And, well, two well-known examples of that are Brownian motion, where I have fluid, a liquid or a gas, and there is kind of, well, micrometer-sized particle, or a few of those suspended, and due to their ongoing collisions with the gas or the liquid molecules, they make some irregular motion, which on a macroscopic time and length scales, on average, can be described by the diffusion equation. Another popular example are Lorentz gases, where I have an array of scatters. It may be a regular array, it may also be a completely random distribution of these scatters, which are fixed in place and time. And then there are light particles, well, that move between them, make specular collisions with these scatters. It may also be a random potential in which these particles move. And again, the average motion of such a light particle can be described on macroscopic time and length scales by a diffusion equation. Good. Now, the assumption that goes into this projection operator formalism is that this macroscopic long time behavior, which can be characterized by, say, some ensemble average delta R minus. So this is some average over a non-equilibrium ensemble. So I don't want to restrict to just one single realization, but I want to look at the average behavior of a cloud of particles or many realizations of the same particles. And this would be n of R and T. Then the Fourier components of this quantity are the average values e to the minus ik R1 of T. And these are the central quantities I'll look at. If you have a system that is on average translation invariant, an infinite system, or a system with periodic boundary conditions, it is always practical to look at Fourier components because they don't mix. Translation commutes with time evolutions, and therefore, say, the different Fourier components for the particle density develop in time independently.
The first equation.
This equation just says that the average density of the tracer particle, 1, can be found by looking at the microscopic density, which you can formally define as a delta function of R minus the position of the tracer particle. So you know exactly where this particle is. The density is completely, say, concentrated in the single point. And that's what the delta function does for you. But now you look at several realizations of the process. You may look at smeared out initial conditions for the distribution. And then the average of this quantity over some ensemble that describes a non-equilibrium system, by definition, is the density of the tracer particle as function of position and time.
The arguments are
yeah, no, that's true. This is R. Yeah, I did that wrong. Yeah, thanks. R1 is the position of the tracer particle, and R is the position where you want to determine the density.
Many different trajectories of your tracer particle.
Yeah.
And you averaged over and see.
Yeah, sure. Good. The microscopic time evolution is described by the Liouville operator. And so the time derivative of function of R1 and T1, and these are the coordinates of my tracer particle. But then there are all the other particles in the system. The Liouville operator acting upon this function, and the Liouville operator is the sum over all particles pi over mi dd ri minus dh dri plus dd pi. Yeah, so I construct the time derivative of this function by taking the derivative with respect to Ri, so ddri, dri dt, where, okay, no electromagnetic fields present, so dri dt is vi, is pi over mi, and ddpi, dpi dt, dpi dt is force on particle I, which I assume can be obtained by taking the gradient of the Hamiltonian with respect to the position of particle I. Instead of looking at the time evolution of function of particle coordinates, I can also look at the time evolution of this non-equilibrium ensemble density with which I want to describe the system, and that satisfies the equation ddt rho of R1 Pn equals minus L acting upon rho R1 Pn. Yeah, this comes from the anti-hermeticity of the Liouville operator. Now you may look at the integral of rho of t f. But you may also describe that as the integral of rho times 0, and then the function R1 at time t, the n of time t, and then you describe this as e to the power Lt acting on f and Pn, and you let the operator act to the left, and then its adjoint operator is e to the minus Lt. And you can take the time derivative in both representations, and one time you get this equation, and the other time you get that.
What is the definition of rho?
Sorry?
What is the definition?
Rho is an ensemble density, so I assume I describe the system not just as such, but always as an ensemble of roughly equivalent systems. And so if I say I have a Brownian particle, which I start off at the origin at the initial time, then first of all the mass is described as a kind of equilibrium distribution of all the other particles, and then the Brownian particle still can be given a Maxwellian velocity distribution. And that will give rise to a time-dependent ensemble density. So after given time t, the Brownian particle is kind of Gaussian distributed in a region around the origin, and this is expanding as a function of time. And so the ensemble resulting from the initial one is the non-equilibrium ensemble, which I have in mind here.
Why is there a minus sign now?
That's because this, this L, if I let it act to the left, I have integral fx ddx. G of x is integral of g of x minus ddx. F of x plus some boundary terms And if I take care that those vanish, for example, because of periodic boundary conditions, then I just get this property. And that gives rise to this minus sign when I switch to the description where I let the functions of all the particle coordinates develop in time. The description where I say, okay, I look at a function of the coordinates and I average them with a probability distribution that is time dependent. It's like Schrödinger versus Heisenberg representation in quantum mechanics. The what?
He's asking what are you consolidating over? Space.
All
Here?
of, no, on the right hand side. This,
All space.
all of, yeah, that integral is over all the base. That's what's
What is e to the LT? All right. that
no,
is-
just the integral on top. So
Uh,
rho t, it's
F-
just asking what you're integrating on.
Oh, okay. This goes over gamma space. So usually that's, and this stands for d R1, d P1, d Rn, d Pn. So over all the position and momentum coordinates, yeah, sorry, I'm a bit sloppy sometimes.
And that's the average of the
Okay, I'll erase this because we don't need it anymore. Good. Now I want to introduce the projection operator onto these Fourier components of the density. And so in this case it's defined as sum of k. I use sum because I want to start from a system with periodic boundary conditions where the Fourier modes form a discrete set. The k values have to be fitting onto the system in which the particle is moving, and t of k and t. Okay? Which, if you write it out, sum of k minus R1 minus where I introduce an inner product, which is given by inner product of f and g, where f and g depends on all the positions and momenta of the particle. The integral d gamma, so it's the same shortcut again for all the coordinates, f of gamma star g of gamma multiplied by the equilibrium distribution, all these positions and coordinates. Often this is done in the grand canonical ensemble where the number of particles is not a variable, but that's just a technical detail. And now notice that this indeed is a projection operator, p squared equals p.
Are arguments in your projection operator the same?
Well,
R1.
yeah, well, you see this is, so this projects onto, say, functions of position of the tracer particle, and these functions are the Fourier components of the microscopic density. And so these functions are the e to the minus ik dot r1. And so for each k I have such a function. I'm summing over all things. Yeah. No, it's not, because I say this is a projection operator acting in the space of all, say, quadratically integrable functions of R1 and P1. And because these functions do not depend on P1, it's an enormous reduction. Yeah, so the momentum coordinates of this tracer particle in principle are also degrees of freedom. And those are completely projected out. Well, this is p squared equals p, and that is because the inner product of nt of k and t, k prime, is delta of k and k prime. But this is 1 when k and k prime are identical, and it's 0 if they are different in at least one of their components. And this is, of course, a result of translation invariance of the system.
Are you essentially projecting onto?
No, I'm projecting onto these functions which describe the spatial density of the tracer particle, but have no information on the...
The basis for a times between position space, time function.
Yeah, so you could say your projection operator in a way is integrating over momentum coordinate.
Yeah, it's integrated over all momentum.
Yeah, that has the same effect basically. But I prefer to write it in this way.
But it is equivalent to that.
Yeah, it is equivalent. And I will also use the symbol p perp, which is 1 minus p. And as always, the complement of a projection operator is also a projection operator. Good. Let us see now what happens to the time. Yeah? Yeah. What additional quantity? Yeah. Yeah. Right. Yeah.
You integrate over all
Yeah,
R1s, right? That will be
Yeah.
Then you're projecting onto that one.
Yeah. And you integrate over the positions and momentum of all the other particles. Yeah.
Are the ones that depend on P.
Yeah.
So you would have to add M functions that also depend on P, like e to the I k
Yeah.
dot R plus k prime dot P, and then some on
Yeah.
R and P.
But also on R2 or P1.
Yes, you're projecting everything over there.
Will only functions in other spaces exactly.
Yeah. So this only say considers function of the tracer coordinates. Yeah, yeah, that's what it does. Right, yeah, yeah. And it will be assumed later on that things that only evolve in this orthogonal space indeed decay rapidly. So we'll use that. Okay, now let's look at non-equilibrium ensembles, which are not too dramatically out of the equilibrium. So they can be written, well, I guess formally I could always do it, but it makes sense if the deviation is too large. It's rho naught times 1 plus delta t. And now I may rewrite it as rho naught times 1 plus p delta t plus p curve. Delta t. Then the Liouville operation of equation, obviously rho dt equals minus L rho. Now rho naught is invariant under time evolution, so L active upon rho naught will give me nothing. And so I may rewrite this as minus rho naught L delta t, where I used still also that rho naught commutes with L, for the same reason.
There's a question back here.
Yeah.
With the F and rho. So F is, as you said, is some kind of a distribution, right, in a phase space.
Yeah.
And rho is seems to be some kind of an observable that way.
Sorry?
Rho is what?
Rho is some non-equilibrium distance. Fairly simple one. Good. I said now delta t equals p delta t plus curve delta t, and I can separate this equation into two equations, one for p delta t and one for curve delta t. Well, p equals P-L. And I used the fact that P, or P, in this specific case, equals 0. And the reason is that if I let L act upon this density, it gives me minus ik times v1. So I get a function which is odd in the velocity. I take the inner product with n, which is even in the velocity, and so on, averaging that in equilibrium ensemble, I get 0. But for general hydrodynamics, that won't be 0 anymore, you'll see. Then the curve delta t And now, the interesting point is that this equation, though it may look a bit complicated, is in fact a very simple equation. It's of the form df dt equals minus af plus an inhomogeneous term b of t. And so that can be integrated immediately, at least formally, p curve delta t equals minus integral from 0 t tau e to the minus L hat t minus tau curve L t delta tau plus an initial value term e to the minus L hat t curve delta 0. And where I introduced L hat, which is p curve L p curve. And so it is this kind of, well, e to the minus L hat t, kind of truncated propagator which throws out at each moment whatever is generated along these supposedly slowly decaying density components. And I will assume that, well, because say what is generated along the slow modes is thrown out all the time, this will decay rapidly in time. And it's essential for that you make the right choice for your projection operator. You forgot no slowly decaying functions of, well, the phase space variables. Yeah. In principle, but PLP happens to be 0.
So just in the term that survives, should the people be on the other side?
Now there's PLP curve, and P curve contains both even and odd functions of the velocity, so that there's nothing that drops out there. It's just this PLP of all the combinations, PLP, PLP curve, and so on, that happens to be 0 in this case. But everything else remains and is not 0.
So somehow the momentum P1 is considered fast decaying, but R1.
Yeah. Yeah.
Why is P1? How should I understand that P1 is? The other particles are light, right? And
Yeah.
This one is heavy.
Well, what can also be, say, a particle which is identical to the other one. So it's not specified. Look at self-diffusion. This would apply just as well.
But somehow, so there was an approximation made there based on separating it into slow and fast.
There's no approximation made. Well, the approximation which I make is that I now assume that this e to the minus L hat t, so this truncated propagator, decays rapidly in time, whatever I let it act upon. But otherwise, these are just formal identities. It's just algebra.
Yeah, right.
Yeah, so it's
Right, but no, I meant that approximation. I mean,
yeah. It's quite essential. So this assumption that these type of things may be neglected for a long time, they have to be justified, and they need not always be satisfied.
But it doesn't depend on having like one heavy particle and the other one's
No.
light or something.
No.
So
And
it's essential to have a perpendicular space where things decay fast. Is that what you're saying? It's called
Yeah.
orthogonal subspace.
Yeah, so
So
I
I projected onto one space, which is my
Yeah.
slow degrees of freedom.
But
which
there's nothing
represents
slow
the
about
slow
that.
degrees.
Right.
So they're not identical to the slow.
Right.
So they're not exact eigenfunctions which decay slowly,
No.
but they are representative for everything that decays slowly. And in fact, if you look critically, you'll find that the average velocity has a slow component as well, but that is driven by the density. So somehow you include that implicitly by this projection formalism.
So the essential thing is to find the right projection operator, which will pick
That's
up the...
that's very essential. Yeah.
And I guess what Matt is asking is for the trace of diffusion, we defined it as a projection.
Yeah, tracer diffusion against, say, an equilibrium background. You may relax that in some cases. You may restrict yourself to the density components of the tracer particle. Although if you look at the fluid, something may happen there in response to the tracer particle. But you assume that you're not looking at that. You just look what happens at the tracer particle. And then the density describes the slow decay. That's enough. Yeah, so there is a lot of wishful thinking in the whole procedure. But it works in most cases. Good. Now I write down some things which are not really needed, but they are illustrated. L e to the minus ik dot 1 minus and I define this as minus ik jt. Okay. And so the current of the tracer particle microscopically would be V1 times delta. This is the current density. And then if I take Fourier components of that current density, I just get these quantities. And then, using that, you may rewrite dt delta t. T equals minus sum. Okay. Then there is a k squared coming from these k's left, right. Integral 0 to t d tau. And a product e to the minus L hat tau. Good. Now I may take an ensemble average of these density components with this p delta t, because, well, the density components are precisely in this space on which I project. I only have to take the inner product of these densities with p delta t. The curve automatically called standing. And t, and use bar now to make an average. Equals, well, if k is 0, then nt of k is just a constant, e to the minus ik of r becomes 1, gives me delta 0, and then this term gives me the inner product delta t. T k, by definition of this. The product delta is a real function. So there's no complex conjugation. d. No, this is a partial derivative. And then introduce a new symbol, u of k and tau. That is u of k t is v.
What is the NTK on the right-hand side of the first line?
This is the Fourier component of the.
Okay, this is the average.
Yeah. Yeah.
So why the NTK doesn't depend on the right-hand side?
Let's see. Yeah, this should be an average. Yeah. I forgot the bar here. Thanks for the question. In other words, this is still a microscopic function. And it doesn't depend on t, at least. Not explicitly. Good. Now, suppose that this u of k and tau, defined here, decays rapidly in time, which in fact it ought to do because it has this time evolution, this truncated evolution operator. Then this nt bar of kt minus tau will hardly change during the time interval that this u vanishes essentially from 0. Which means that I may replace here the nt bar of kt minus tau by nt bar k of t and perform this time integral over u. And that gives me a diffusion equation of the type.
Are you assuming periodic boundary conditions?
I'm assuming periodic boundary conditions all over. Yeah, and if in the end you can make a limit where system size goes to 0 and you go to uniform infinite system. T equals minus k squared d k and t bar. T where d k is the integral 0 to infinity u and t. And now I want to make a remark which I will not give derivation for. It is easy to express this function u, which gives the time evolution or current correlation function with this truncated time propagator, to express that in terms of an actual current time correlation function c of k and t, which is defined as k e to the lt, so the actual time evolution operator j k. So this is an equilibrium time correlation function of the exact particle. If you introduce Laplace transform, f of c equals integral 0 to infinity t e to the minus z t f of t. And it's easy to show that u of k and z equals c k z to the 1 minus k squared over z times c k z. And now what you see is that if at fixed value z you take the limit k goes to 0, then u of k and z becomes identical to c, k, and z. Because this term drops out that limit. And so u of 0z c. And from that we may conclude that the limit to k going to 0 okay, is the integral from 0 to infinity dt averaged over an equilibrium ensemble. But I have to add the remark that if this exists, because there are situations in which this integral is diverging, and then of course the diffusion coefficient doesn't exist.
Does that have any physical interpretation?
Sorry?
The diffusion coefficient diverges. Does it have any physical interpretation?
Yeah, it does. Sure. It means that, say, the mean square displacement of a density profile spreads with time faster than the square root of time.
Does it mean any kind of critical phenomenon?
It's related, but it's not necessarily critical phenomenon. So in 1- and 2-dimensional fluids, this will always occur. And that's not at all critical. It happens at low densities, although it's a small coefficient there. But it's similar to critical phenomena. And also this mode coupling theory, which is used to describe it, was first developed for critical phenomena. But it turns out to be very useful also just for time evolutions.
Does it have to do anything with Brownian?
Well, Brownian motion is one example where it can be applied, but it doesn't require any Brownian motion. It's much more general. So it's one example of Brownian motion. Good, although it's not really needed. But I want to show you that, well, this result, this is known as the Green-Kubo formula for the self-diffusion coefficient. Yeah.
Under what limit it becomes a non-trivial?
What?
Under what limit it becomes a non-trivial? Like a usual diffusion.
This is usual diffusion.
But you have a memory control.
Sorry?
That is the integral, right? It's a memory control.
Well, you see this limit k to 0, it says there can be a k dependence of the diffusion coefficient, which means, say, if I have, say, an initial density profile, an excess density profile, which is sinusoidal. It will decay according to the diffusion coefficient equation as e to the minus dk squared t. Now, you may find that if you go to very short wavelengths, this d actually depends on k. And usually say the length scale on which you can create these oscillations is so large that decay dependence doesn't occur. But say if you would make a density, say perturbance with laser light or something, you might hit a region where this decay dependence does become important.
So is there a simple generalization of this for that case? K is not zero?
Well, this is the generalization, in fact. So you get this Green-Kubo coefficient which depends on K.
Is it the Laplace transform of that point function? Or?
Let's see. It is. So it says that d of K is basically the integral to 0 to infinity dk d 0 dot k e to the minus ik dot r minus r0. Yeah, so this term is usually neglected because it's so close to 1 over the range where, well, you have to take it into account that you may replace it by 1. But yeah, if you have very strong oscillations, that may not be justified and you get something. But you have to, let's see, you have to do this relationship between D and U with a bit carefully, but it's all well defined. Oh yeah, that's really, yeah. Because I made this approximation that, say, n of kt minus tau is replaced by n of k t. But I need not do that. If I keep that in, I do get z and k dependent to do k and omega if I prefer. Sure. Good. I want to show you that perhaps Green-Kubo should be assigned to Einstein, because Einstein had this relationship d equals limit t to infinity x1 of t minus x1 0 squared divided by t. But if this limit exists, if the next limit exists, it should be the same as half the limit of t to infinity d dt of x1 t minus x1 0 squared. Yeah, so the idea is that this behaves as 2dt, but if I take the time derivative of something that behaves as 2dt and time derivative has a limit, that limit necessarily has to be 2d, so this will give me the same result. Now, I can commute the time derivative with the equilibrium average because that's time independent. So this is half limit t to, right, to infinity d1 of t times x1 t minus x1 0. I'll rewrite this as the integral from 0 to infinity tau d1t d1 tau. The displacement is nothing else than the time integral of velocity. Then do a time shift, so this only depends on the difference t minus tau, and you're back to this Green-Kubo result. So Einstein is a little bit more general because there are cases where this will exist and this will not. Say if I take linear combination of a linear function plus a cosine, then dividing by t will throw out the cosine, taking the derivative will not. But except for those, it's identical. Good. Then comment this Green-Kubo expression may be divergent. We mentioned that. We saw that already. It may also be zero. This may correspond to cases where, say, the density profile expands in time, but it goes with a slower power of time than 1/2. There are examples where it goes as t to 1/4. That's subdiffusive behavior. But in these cases, both the case where it diverges and the case where it's zero, this generalized diffusion equation, which we have here, still makes sense. So you can still use that and also see what happens in these sub and super diffusive cases. Then, what I said already before, additional slow modes could spoil the argument. So here, the risk is maybe not so high. This hydrodynamics, it's a lot higher. Then, final remark, formalism also works for stochastic or stationary non-equilibrium systems. So I've assumed here all the time that the background is equilibrium. It may also be in a stationary non-equilibrium state, and you can still apply this formalism. But you have to make proper substitutions for the Liouville operator, certainly in the stochastic case, and you have to replace rho naught by the proper non-equilibrium ensemble. Good, then time is running out, but I can still sketch how this goes in basically the same way for hydrodynamics of simple fluids. And K equals sum J, which runs over all particles, e to the minus ik ij. Then there is the momentum density, d of k, sum j minus ik ij, and then the momentum minus j. And there is the energy density, sum of j e to the minus ik rj epsilon j. Where epsilon j is the energy of the particle j, well, at the time and position where you look at it. And it's given by kinetic energy, dj squared 2m, plus in the simplest case where I have isotropic pair interactions, the sum over L by JL by JL. But of course this can be generalized immediately in case of more particle interactions or interactions which are not isotropic. Let's keep this in mind. Good, then other hydrodynamic fields can be expressed in terms of these. So you see that, well, you typically, because the starting point are the conservation laws, you start from the number density and the energy density. But sometimes you want to use temperature, entropy, pressure. And those can be defined like T of R and T equals T naught plus T, the N R and T. E constant plus dt, use epsilon here, the epsilon and constant epsilon R and T. And so just linear expansion of these hydrodynamic fields in terms of this N and epsilon. And that way you can also, without any problem, define an entropy density because it's completely determined by the equilibrium partial derivatives of entropy with respect to density and energy density. Then I will combine these things into the d plus two-dimensional vector, psi, and the Fourier components will be given by n g epsilon. Okay, so 1 plus 1 plus d. And for these, I can introduce a susceptibility matrix. Phi ij j equals the inner product of psi I k psi j. Okay. Sorry?
Some kind of potential.
Yeah, phi is let's see, this is double. Okay, no. Yeah, so I assume that the Hamiltonian is sum ej squared over Tm plus sum of j smaller L phi RJL.
The epsilon is the eigenvalue of H.
Sorry, epsilon, yeah, that's the energy of particle J, where I make the convention that the potential energies are distributed equally among the particles that participate. So you could do it in a different way, but it doesn't. In its essence, it makes a difference. And then I can introduce an adjoint factor, phi of k, psi of k. And I'll use an open dot for an inner product within this space of d plus 2 variables. And have to take the inner product with the inverse matrix of the chi matrix. So phi j sum over L psi L phi inverse of J, and strictly taken, I have to take the complex conjugate of that. Although in the limit k to 0, chi becomes real, and usually you only use the k equals 0 values. And then what you have to find is that psi L in a product phi j, okay, equals phi j j L, okay, equals L. And projection operator onto the slow modes now can be written as sum of k psi k dot phi k or alternatively sum over k by k plot psi k.
In the first line here, is the sum is over J or
C by L. This should be sum over L. Yeah. Yeah. Thanks. Good. This can be written in two alternative forms that are a bit more appealing from, well, recognized thermodynamic densities. One over the volume, sum over k. There, beta of R and T, 1 over Boltzmann's constant times T, R and T, and mu R and T. Beta R and T, mu R and T. And mu is the chemical potential.
How did I get to introduce data and mechanical potential from there?
Yeah, well, that requires some thermodynamics and some algebra. It's in the notes, but I don't want to. However, you may notice that I can flip all these things. I may also write it as mu n, well, this is symmetric, and then beta epsilon. Then there's an alternative form which leads more directly to the Navier-Stokes type of equations. Beta not d and not nk. P of k, where free is the pressure, plus 1 over m g. G. That is dot an ordinary inner product in Cartesian space, plus, no, we have that, and not squared T is just the temperature field, so deviation of temperature from its equilibrium value, and sigma is the, well, Fourier transform of the entropy per unit mass. Now the derivation of linearized hydrodynamic equations goes like the derivation of the diffusion equation. Set again rho of t equals rho naught times 1 plus p delta t plus curve delta t dp delta t dt is minus p t minus pl curve delta t d curve delta t dt equals similar equation. You integrate the second equation and you substitute it into the first one. And okay, thereafter some algebra, which, well, I think we can take time for that. You end up with equation form the psi average of t equals phi average of k and t dot okay. As I announced already that for hydrodynamics, PLP doesn't vanish, and well, this is so plus an integral 0 t off curve also you get terms that are of order k, so gradient terms, which come from this term, and terms which are of order gradient squared. And these are again current correlation functions. Good. I think I'll go directly to the Navier-Stokes type of equations that come out. There's first of all the continuity equation, which is minus ik m g t. This always holds. This is just mass conservation. The G average, okay, T. So this is the Navier-Stokes equation. It's minus ik d bar T. So it's the gradient of the pressure. This comes from this psi L psi term. Then minus k squared n naught m, That's the mass density in equilibrium. Eta of K tau. And then there is a longitudinal velocity contribution plus kappa of K at tau plus d minus 2, 3 eta of d of K and tau. K hat is a unit vector along the direction of the vector K. And then there is, well, a term which usually is neglected, so I'll leave it out. It vanishes in limit K going to 0, but it gives contributions possibly. So a coupling to between the momentum current and the heat current. And where eta of K T, eta naught D, then in a product K dot. L hat is a unit vector that is orthogonal to K hat. P of K is the microscopic pressure of the system, the Fourier components of that. No, sorry, I'm mixing up. E to the L hat T K hat and, well, kappa of K and T plus 2D minus 1 D minus eta K. Well, it's the same expression beta naught of B dot as K hat D K hat. Okay. Okay. Well, there's more expressions. It's a similar equation for the heat conduction. D is the dimensionality of the system. So it's 3 in 3 dimensions, 2 in 2 dimensions. So
like the area strip situation is a problem for all dimensions?
The convergence?
Yeah, in existence of laws.
Let's see. Oh, the solution of the hydrodynamic equation. Well, that's the nonlinear hydrodynamic equations. And those do not follow from this formalism. That there are generalizations by Zwanzig, for example, to nonlinear equations. It's very complicated projection operators. I never found those very appealing. They're intuitively clear. What you get by this green Kubo formalism are only linearized, say, versions of the hydrodynamic equation. Plus, these things are not in any way rigorous. So they assume this is the set of slow variables, and then that's the equations we get, and these are expressions for the transport coefficients. But there are many, many assumptions, and they're not always fulfilled. Good, let me skip the further equations and just make a few observations. All these equations are expressed in terms again of temporal convolutions of hydrodynamic fields with current correlation functions. If the latter decay rapidly, then the tau dependence of this, say, g of kt minus tau may be neglected again, and you're back to the usual form of the hydrodynamic equations. But if these current correlation functions decay slowly, you may have to stick to these convolution forms. And ordinary hydrodynamic equations may not be fulfilled, which is the case in 2 and 1 dimension. Again, the truncated correlation functions can be expressed in terms of full correlation functions. It's a bit more complicated algebraically, but works. Green Kubo expressions for transport coefficients are very nice formal expressions, but if you want to calculate them analytically, you still need something like a Boltzmann equation, usually a strong approximation scheme to come out with anything specific. But for computer simulations, they are very useful. And they are one of the standard ways of computing transport coefficients. Positivity of transport coefficients follows directly, although not yet. Oh, no, there's no question. You can't prove that they can't be zero, but you can prove that they can't be negative. Now, Onsager symmetries between transport coefficients, especially in mixtures, follow immediately. Linear response to external fields, especially electrical currents and so on, can be incorporated in the same formalism. Extension to quantum mechanical systems is straightforward, but the choice of slow variables may have to be adjusted. So there may be additional conserved quantities like charge of magnetization or whatever. You have to include the densities of those. But very importantly, there can be macroscopically broken symmetries. Think of liquid crystals where you get a director field which can vary from place to place. And it's not related to any conservation law. Still, it is very slowly changing. So if that happens, you have to include those among the slow variables. So that's very often the case with statistical mechanics. You require something like ergodicity. You find in certain systems it's not satisfied, and you say, all right, then we require ergodicity on a subset, and still use the same formalism. And the same here. Good. I thank you for your attention. I think it's time for a break.